Hello. We continue to talk about factors affecting chemical reactions. And big part of it is the energy transfer that occurs during the reaction. In fact, in many cases, in most of cases, the energy transfer and exchange of energy is the big driving force behind the reasons for the chemical reactions to occur. So over here, we will talk about this reaction of combustion. Let's start with this one. Well, methane, this compound over here, reacts with oxygen, burns, to produce carbon dioxide and water. Okay, inside of any chemical compound, inside of chemical bonds of chemical compound, there is a certain amount of stored energy, potential energy. Let's say inside of the chemical bonds of carbon and hydrogen and inside of the oxygen molecule at the moment together, all of them contain about 1000 kilojoules of energy. Then reaction takes place and our methane and oxygen rearranged into carbon dioxide and water. And if we go around and measure the amount of energy stored inside of carbon dioxide and water together, we will find out that there is only 110 kilojoules of energy that is there. So pretty much 890 kilojoules energy disappeared. Well, we know that energy cannot be created or destroyed, but energy can be converted into different forms of energy. So any guesses where all the energy went? Well, it was converted into heat. Nobody really wants to place a hand near the open fire because it's very, very hot. You can get burned. This is where all that energy went. Potential energy that was stored inside of the reactants was converted into thermal energy of the heat coming out of the reaction. So over here we have heat as a part of the product, of this reaction. What is formed? Carbon dioxide. What is formed? Water. And what is formed? Considerable amount of heat in the process. We can now represent this process as 1000 kilojoules of energy stored inside of the chemical bonds of the reactants, converted into 110 kilojoules of energy stored inside of carbon dioxide and water, and the remaining heat that was released in this reaction. Energy cannot be created or destroyed. Don't forget that. So over here, energy is released. Energy is part of the product. So is this process exo or endothermic? How would you describe it? Pause the video and answer this question. Okay, I hope your answer was exothermic. Exothermic is the type of reactions where energy is released as a result of this reaction in the form of heat. So if there's any mnemonics that I would suggest, exothermic, heat exits matter, so energy is released. Okay, so it's time for us to talk about this specific term, heat of reaction or enthalpy. This is the term that describes that energy that was released in the reaction. Heat of reaction or enthalpy. Both terms are used interchangeably, so be ready to recognize both of them. The symbol that we use to identify them is delta H, heat of reaction, is the difference in the amount of potential energy of the products and reactants. So what it practically saying that enthalpy, heat of the reaction, is the potential energy of the products minus potential energy of the reactants. If we go back to our reaction of burning methane, and we will see that 1000 kilojoules converted themselves into 110, we can calculate the enthalpy, the heat of reaction, as 110 kilojoules, potential energy of the products, minus potential energy of the reactants, 1000 kilojoules, which gives me negative 890 kilojoules. So the amount of energy released was 890 kilojoules. This negative sign is very important. It actually shows me that the products had less energy than reactants. The negative side for heat of reaction identify every reaction that is exothermic, that had energy coming out of it. Whenever I see heat of the reaction being negative, I immediately know that this particular reaction was releasing heat. It was exothermic reaction. So whenever is enthalpy is below zero, reaction is exothermic. Vice versa, whenever we have heat of reaction being above zero, we know that the products had more energy than the reactants, and the reaction was endothermic. During that reaction, energy was absorbed. Okay, now here's a challenge. 3 reactions. Tell me, which one is exothermic, which one is endothermic? Okay, I think it was easy. Endo, exo, exo. But I'm sure you should feel a little bit confused because you couldn't have told which one is exo or endothermic just from the reaction themselves. That was a trick question. Reactions themselves do not tell you if they are exo or endothermic. You need more information about them. Okay, so how did I know that? I didn't know that by the second side. I knew it because I knew how to read this special table, table I. Okay, pause your video and right now dig in your backpack and find your reference tables. Once you found them, find this particular table right over here. It's a table I, and then come back and continue to listen. Okay, I hope the reference table is with you and you are looking at your own personal table I. Let's look at these reactions over here. The first one, nitrogen reacts with oxygen to produce nitrogen monoxide. Look at the enthalpy. This is my heat of reaction right here. Here's the indicator. And it is positive. This positive sign tells me that this reaction over here is endothermic, that during the reaction of nitrogen and oxygen, some energy has been absorbed. And eventually, nitrogen monoxide has been created. And the amount of potential energy stored inside of this molecule is 182.6 kilojoules more than all the energy stored inside of the nitrogen and oxygen taken together. Okay, let's look at the second equation, carbon and oxygen forming carbon dioxide. This reaction has heat of the reaction being negative. It immediately tells me that inside, as a result of this reaction, there was some energy released along with the formation of carbon dioxide. About 393.5 kilojoules of energy has been released. Energy part of the product for this reaction. And the last reaction is here between nitrogen and hydrogen. Once again, I end up with the negative heat of reaction, which tells me this reaction, the result of this reaction, has been releasing along with the ammonia some energy. Well, specifically about 92 kilojoules of energy has been released as a result of it. And these two reactions are exothermic, while this one over here is endothermic. All right. Now, let's dissect the endothermic reaction and see how it works for the endothermic reaction. We already know from table I, this one is endothermic reaction right here. Let's say my nitrogen and oxygen together contain about that many kilojoules of energy. When they rearranged into nitrogen monoxide, this product contains 1200 kilojoules. So some energy has been absorbed. Without this extra energy, this product would not have been created. It's not only about initiating the reaction, it's also about providing this extra energy to be stored inside of nitrogen monoxide. Without it, this reaction would not even occur. Heat, in this particular case, is part of the reactants. Without it, just like without oxygen and nitrogen, this entire reaction would not be taking place. So we can rewrite this as this information. Here is my energy for the reactants. 180 kilojoules has been absorbed, maybe from the surrounding. And eventually we have a product that contains that many kilojoules of energy inside of its chemical bonds. Okay, so energy is absorbed in this reaction, so we're talking about endothermic reaction. And if we calculate the heat of the reaction, it will be energy of the products minus energy of the reactants. It is positive 180 kilojoules. The positive number over here tells me that this was endothermic reaction and 180 kilojoules has been absorbed by oxygen and nitrogen in the process of their remodification into nitrogen monoxide. So whenever we have positive enthalpy, we're talking about endothermic reaction. Now, it is time for you to get practice with the table I. Please look at the table I, look at these 6 reactions, and identify them as exothermic or endothermic. Pause the video, identify all the reactions, and then unpause the video again. Okay, I hope you did exactly what I told you to do. So you did identify those reactions. And now check with my answer kit that I prepared for you. The first reaction is endothermic, exo, endo, endo, exo, exo. I hope you have the same answers. If not, go back and listen to the explanation once again. Now, I can identify these reactions as exo and endothermic with the words, or I can actually write the symbol of heat on the appropriate side of the reaction. If you think about it, here is my endothermic reaction, meaning that the heat should be somewhere among the reactants. Heat is needed here to eventually be transferred into the bonds of hydrogen iodide. On the exothermic reaction, my symbol of heat would be on the part of the products, because it will be coming out with the products being alongside of the products being formed. So for my amusement, I can rewrite this reaction in this form. My word heat is written either on the part of the product or of the reactants when energy is absorbed, and on the part of the products whenever energy was released. I also have a challenge for you. Over here, I wanted to point out of these 6 reactions that we started to talk about, out of these 6 equations, only 4 represent true chemical reactions. There are 2 equations that represents a physical change and not a chemical reaction. So, can you guess which equations represent a physical change, not a chemical reaction? Okay, I will reveal the answers at the end of the video. Right now, I want us to go back to our representation of the heat. Well, I can leave my equations like this, and admittedly, usually we do skip this, we do not identify heat, but right now for our conversation, for our understanding of how reactions and physical chemical reactions and physical processes transfer the heat, it is important to have it here for our conversation's sake, so we would know what we're talking about. I also can go forward and go check the reaction table I, and even put in numerical values how much heat has been absorbed or released. I took those numbers from table I. I know that inside, during this reaction, 53 kilojoules of energy has been absorbed. And during this reaction, 3,351 kilojoule has been released. Every single time I check the heat of the reaction, the change in the amount of energy, and the sign of the heat of the reaction value tells me whether energy has been absorbed or has been released. Okay, I want you to remind you that the reaction themselves, just looking at the reactions without information about the heat of the reaction, would not give you the idea about which reaction is exo and which one is endothermic. Okay, going back to my mystery equations that do not represent a chemical reaction. Well, I hope you guessed it's number 4 and number 6. Look at this. Potassium nitrate solid has been dissolved into aqueous solution of potassium and nitrate ions. It's a physical process. Dissolving something is not a chemical reaction. It's a physical process. And so the same thing can be said about our sodium hydroxide. The solid has been dissolved. It was turned into solution of sodium hydroxide. This is a chemical, is not a chemical process. It is a change of a physical state. So these two videos, this and previous one, supposed to serve you well to answer the first set of questions. And I hope you do it on time. Bye.